I'm going to be talking about EMPs and CMEs, electromagnetic pulse and coronal mass ejections. There's a lot of misinformation out there, and I think it's actually comical how much, you ask 10 people on YouTube what an EMP is, we'll get 20 answers, 20 different results. So I'm going to dispel some of the misinformation that's out there. And so let's go on from here. And I don't know how you want to do this, Anthony. We'll take questions after the fact, or we can stop in the middle. It's up to you.
We can do them at the end. That'll be fine.
Okay, fantastic. So let's start off with the very first question. What is an electromagnetic pulse? Well, an EMP is an electromagnetic pulse caused by a detonation of a nuclear device. It's typically a nuclear weapon. An HEMP is similar, but the nuclear device is detonated in the high altitude. So for it to be an HEMP, which is where the bad guys really are targeting, it needs to be 150 to 300 miles above the Earth's surface. So an HEMP is a high altitude electromagnetic pulse. And the reason why it needs to be so high is a nuclear detonation uses kind of like a line of sight. So the higher it is, the more area of the U.S., for example, that the effects will be felt. There are three parts or kinds of waves that are produced during an EMP pulse, and we are going to talk about those. These waves are called E1, E2, and E3, and I'm sure everybody has heard of this from one in the past. So we're going to discuss each one and how they are similar to this right here, a coronal mass ejection, a CME. A coronal mass ejection is a significant amount of plasma that is released from the solar corona. They often follow solar flares and are normally present during a solar prominence eruption. They are beautiful when you take a look at them. I absolutely love seeing them, but holy moly, they are... if they're pointed at the Earth, we'll have some problems. So the plasma is released into the solar wind, and if directed towards the Earth, it will produce an E3 type of wave. So similar to an EMP, with the exception of it will only produce an E3. And we're going to talk about each one of those waves, including the E3. So here's a pic of a CME that's happening. Billions of tons of particles is ejected from the sun. So obviously light travels at 300,000 kilometers per second. This will take days to reach the Earth because it's not light, they are actually particles. So when a CME happens, it takes a while for it to travel through space. As a matter of fact, here is a action of a CME that's happening, and you can just see the billions of tons of product that is leaving the sun. It's not bad if it's not pointing towards us, but if it's pointing towards us, then bad things can happen, and we're going to talk about that. So the question is, what's the difference between an EMP and a CME? Some people use those terms interchangeably, and that is incorrect. Whoop. Okay. Since both types of events produce electromagnetic waves, only the EMP and consequently the high altitude EMP produce E1 and E2 waves. Okay, there's the differentiator. Both EMPs and CMEs produce E waves, E3 waves. Both types of events can bring the electrical grid completely down, requiring many years to potentially rebuild. So even, and I will say, the difference between the E1, E2, and E3 waves by magnitude order of destruction, the E1 is the worst, and even the E3, which is the least, in my opinion, it's the second worst type of wave out there. It can take the grid down, and we're going to discuss why that happens. So, I've talked about the E1, E2, and E3 waves. What the heck are they? Well, I'm going to show a graph that describes the three parts of the EMP pulse, the E1, E2, and E3. And you'll notice that the HEMP waves are on a logarithmic scale showing both induced voltage amplitude per meter versus time in seconds. And this diagram actually shows it. And I'm going to turn on my laser pointer here and bring this up just so I can describe what we're looking at. This side of the chart is showing volts per meter, okay? The x-axis is showing time in seconds. And as you can see, 10 to the negative 11 is 1/100th of a nanosecond. So it's very, very, very quick. There's 10 to the 9, which is a nanosecond, 1/1000th of a second. And we go all the way up to 1,000 seconds. So that's 10 to the third. And you can see that each wave is created and doing a couple of things. One, it's happening at a particular time frame. And you can see with the E1 wave, it is happening really quick. As a matter of fact, right upon the explosion of right at the detonation point, just a few trillionths of a second after that, this E1 wave is produced, and we're going to see that it only takes about 5 nanoseconds for the wave to achieve this 10 to the fifth, almost 10 to the fifth volts per meter that is produced up in the ionosphere. And we're going to talk about why that's significant. And then you can see the E2 wave is starts at the same time, and but they intersect. And it's not as powerful as the E1 wave, but we're still talking about 100 volts plus for a number of parts of a second. So until we get to the 10 to the negative 3, which is a microsecond, a millisecond, I'm sorry.
Second.
And the E3 wave is the long wave, and it lasts for a long period of time. And so just keep this chart in mind when we talk about that. Now, here's something that you need to keep in mind with every slide from here on out. The data that I'm showing is for EMPs that were produced during the 80s and 90s, okay? Today, countries have thermonuclear devices 10 times more powerful. As a matter of fact, there are thermonuclear devices that are designed to give very little destructive power when it's exploding. It is designed to produce the best and most significant EMP wave out there. So what I'm describing to everybody is kind of old news. The problem is, right since Starfish Prime happened, the nuclear test that we were involved with, everybody signed an international agreement that there'll be no more testing in space and no more ground-based type of test. I say that because in today's world, we really don't know what's going to happen if a country sends a EMP-directed blast to the U.S. As much as what we'd like to think, it just is not the case. So let's talk a little bit more about the E1 and discuss why it is so detrimental to to our electronics. So the early time wave, the E1 wave, that is the thing that destroys the electrical transmission lines, transformers, specifically electronic and electrical equipment, whether it's connected to the grid or not. And that's the killer, in air quotes, that we'll see with E1. It is the thing that causes the most havoc. It has the wave shape of like I already explained, a double exponential with an extremely fast rise time of about 5 nanoseconds and a mid decay time of 150 nanoseconds. So extremely, extremely fast. And here's where the problem comes in. It can induce up to 50,000 volts per square meter on electrically conductive material at ground level. So this is why the E1 is so detrimental. It produces a huge voltage spike very quickly. So quickly, it does not give time for our normal surge protectors to protect against it. That is why it is so detrimental. Plus, it takes out the transistors and the microfibers that are connecting all the CPUs and that type of stuff. So it destroys the electronic equipment in the processor itself, in other any electrical trace. It can fry them. The E1 produces what's called the Compton effect. And what's happening is when the E1 is produced, gamma radiation from the nuclear detonation ionizes or strips electrons from the atoms in the upper atmosphere. That is the Compton effect, and it results in what's called the Compton current. So there's a current that is produced from this. These stripped electrons travel in a generally downward direction at a relativistic speed of a little bit better than 90% of the speed of light. And this is why the higher the EMP is, the more detrimental it is, because more of the U.S. can be affected, and we'll take a look at a map on that. So in the absence of a magnetic field, this would produce a large radical pulse of electric current propagating outward from the burst location, confined to the source region, or the region over which the gamma photons were produced. So it produces a huge electric current. The E2 pulse. The E2 pulse is an intermediate time, and it's a wave that overlaps the E1 curve, and we already saw that, and it resembles a lightning strike lasting to a couple seconds. It can induce about 100 volts per meter in conductive material. Okay, we can very easily protect against that. But here's the problem with having the E2 follow the E1. According to the EMP Commission, the main potential problem with the E2 component is the fact that it immediately follows the E1 component, which could have damaged the devices that were normally used to protect against electrical strikes, right? Lightning strikes. So that is why the E2 pulse will come into play. Another thing that happens with the E2 is it produces quasi-DC currents, and when you apply DC currents on AC equipment, which is what the power grid is, you're going to have all kinds of issues. And I don't need to go into detail of what happens when DC currents are applied to AC circuitry. You get this little blue smoke that comes out. Then you have the E3 pulse. This is called the late time wave, and it resembles an energy surge lasting several minutes. The surge will affect electrical equipment if it is connected to the power grid. This is the portion of the EMP that mimics a CME, or a coronal mass ejection. Very easy to defend against an E3 wave. The problem is the E2 and the E1 come before it. So again, the fast rise time of the E1 pulse is the thing that causes the damage. And here's an example. We have a 6-foot long electrical cord. It could receive up to 100,000 volts by such a pulse. A 6-foot at 50,000 volts per meter. A meter is about 3 feet. So that's where they get the 100,000 volts. A 4-inch cell phone could receive as much as a 5,000 volt pulse in a blink of an eye. So this is why our electronics are going to be fried, because we're not, if it's not being protected, this is what potentially could happen. So we actually had a CME that was quite significant. And if you already know this, you should. The largest recorded geomagnetic event that happened resulting presumably from a CME that hit the Earth's magnetosphere was the solar storm of 1859, known as the Carrington event, which is one of the scientists, the astronomer, Mr. Carrington. He had a partner that also saw it, but Carrington is the one who is receiving credit for it. Anyway, he noticed it a day or so before it actually hit the Earth. And so what happened? Well, it took down many parts of the U.S. telegraph network. It started fires, and it shocked some telegraph operators. As a matter of fact, some telegraphers, on the other hand, were able to continue operating with their batteries disconnected, powered alone by the induced currents in the lines with a normal or improved signal quality. As a matter of fact, there was an operator that was between Maine and Portland, Maine and Boston, Massachusetts. They were conversing and they were saying, okay, turn off, when this happened, disconnect your batteries. And when they did that, the communication was actually lots better, and it lasted for nearly 2 hours without any man-made power supply. Life as we know it in America could end in seconds if an enemy were to launch and detonate a nuclear weapon high over the center of our country. It is estimated that a successful high-level electromagnetic pulse could be 1 million times more devastating than a 9/11 attack and could literally decimate America. I think we know this. It would fry the nation's electrical grid and the circuitry that powers our homes, businesses, hospitals, phones, cars, plays, traffic lights, ATMs, water supplies, and anything else not hardened against such an attack. Dr. Graham, chairman of the Commission to Assess the Threat to the U.S. from Electromagnetic Pulse, testified to Congress that within a year after an attack, that nearly 2/3 to 90% of all Americans would be dead from starvation, disease, or from freezing to death. Kind of scary. Following an event of this type, life would become even more difficult than it was for those living in the 1800s. And you're asking me, why are you saying that? We live in the 21st century. Well, the people in the 1800s already lived near farms. They lived on farms. They had horses for riding, working on their farms to produce their own food and provide their own transportation. They had their own water and fuel sources nearby. Fast forward to 2025. What do? Well, 35% of our food is imported. 2% of the U.S. population produces food that 100% of the population eats. So there's kind of a problem there, isn't there? Manufacturing plants and businesses would be closed. The stock market and bank transactions and records would be lost. It can become quite messy. As a matter of fact, if you've read 1 Second After, which was based on the Commission to Assess the Threat to the U.S. from Electromagnetic Pulse attack. It describes in graphic detail in a fiction format what will happen. I think I've read that book 20 times, and it's amazing what you can learn from there. Now, I am not saying all of this to scream that the sky is falling and that there's nothing we can do. That's not the purpose of this presentation. All I'm doing is just showing and letting people know what the possibilities are. So the national recovery following an EMP is going to be very slow. Why? Well, there's thousands of transformers in the power grid, with about 300 being hypercritical. Most of the critical ones have no spare or backup parts. They are not manufactured in the U.S., and some have an order wait time of 1 to 3 years. Also, our civilization has become very interdependent. In order to make repairs on the power grid, for example, there needs to be a working telecommunications system. But telecommunications requires the power grid to work. The financial network must operate to maintain the economy. We need the transportation system, roads, streetlights, control systems, etc., just to get people to the failed powered telecommunications and other systems. Without the existing infrastructure, the military would also find it very difficult to operate, even though some of the military equipment have been hardened against EMP events. And I just want to know who thought that was a good thing to have to rely on someone else to repair a catastrophic event to our power grid. You know, I know that Obama and Trump, they have both tried to get things going on that front, but the problem is it's the power companies who are mostly privately owned that they don't understand that it takes. It's estimated about $100 billion to completely, I won't say EMP proof the power grid, but to have enough spares so that if it were to happen, we could get up in a relatively short time. But that money has to come from somewhere. By the way, we spent $100 billion just on the Ukraine war. So the money's there if our leaders really want to put it there. So let's talk about the EMP coverage area. So the area of EMP coverage depends on the altitude which the detonation occurs, like I've already said. Even though it can be expected that not all EMP strikes would be successful or that they would be directly detonated overhead, I would plan as if they would be. So here's a map of the U.S. Let me bring up my laser pointer again. Let's say that ground zero is right in Nebraska, and it's 30 miles up in the air. Well, that would be a lousy altitude to have the detonation, because the radius effect would only be less than 500 miles for the effects of EMP. At 300 miles, however, it would take practically the entire continental U.S. into Canada and Mexico. So 300 miles is a scary altitude for an HEMP. There is misinformation galore. I don't think I need to say anything about that. There are dozens and dozens and dozens of YouTube videos that discuss EMPs and how to protect from them. And that's the scary thing about it. Misinformation can cause you heartache because they're not going to be around if an EMP happens, and the stuff that they tell you about is proven incorrect. They just are regurgitating what they are hearing. As a matter of fact, there's famous people who they get onto the bandwagon and they will go ahead and start telling people all about EMPs and how to protect from them. And then you get people who use this uninformed source to propagate this misinformation. Let me just show you a perfect example of this. And I'm going to just briefly talk about a Dennis Quaid and Tucker Carlson interview. This is just a small snippet of this particular interview. And I want you to listen carefully to what he says. And I'm hoping my audio comes through.
Take out not only the electricity, but all of our entire infrastructure and our society runs on electricity. We don't know how to live without it. You turn on, there wouldn't be any water in your tap. You couldn't get gas for your car because the whole system is broken down. Everything that we rely upon would be gone. The food would melt in our refrigerators. There would be and they predict within a year, about 90% of the population would be dead from starvation, disease, or, people, it gets back to the Stone Age again.
So Dennis Quaid is talking about a CME, not an EMP, but a coronal mass ejection. And did you hear all of the misinformation that he propagated? The good thing is he's a great Hollywood actor. I love his movies. As a matter of fact, my brother, he was a stand-in for Dennis Quaid in one of his movies. So I kind of have a thing for watching Dennis Quaid. I love him as an actor, but like many famous people, they are not the right people to be discussing things that they are not familiar with. The good thing, however, is he's bringing about awareness, and if anything else, I give him 10 stars for doing that. He's actually talking about a film that he produced called Grid Down, Power Up, and if you have a chance to find that on YouTube, I definitely watch it. There's the majority of it is okay as far as factual, but it's still worth watching. So there's a couple things that he talks about. At the 2-minute 40-second, he says that they predict within about a year of the 90% of the population would be dead from starvation and disease. And that is simply not the case. He's conflating CMEs with EMPs. Okay? It's an EMP that would cause 90% of the population to not survive, not a CME. The Tucker Carlson interview is only about the 1859 Carrington event and the potential of another CME from happening. But because people use CME and EMP interchangeably, you get this misinformation. So the good thing, like I said, is Dennis is producing awareness, and I think that is worth credit points there. Now, at the very end of this presentation, I have all of the other inaccuracies that Dennis was propagating, but I'm not here to crucify Dennis. I think he's doing a great job in doing what he can to produce awareness. So I'll just let it go at that. So the question is, how do you protect yourself against a high altitude electromagnetic pulse or a CME? Well, you can't. Now the good news is, I'm kidding. You can sort of. The ideal solution would be to have your entire house shielded. There are some governmental agencies that do that. I know the IRS in Ogden, there's only so much I can say about this, but they are inside of an EMP-proof building. The cost of doing this, however, would be as much as the home that you're trying to protect. So for this reason, you need to identify and shield your critical pieces of equipment that you want to survive following an EMP strike. Now, ideally, these critical items must remain operable no matter how intense the EMP signal is, and no matter when it occurs. And this is the what's the right word? This is the art of protecting yourself from an EMP or a CME, knowing when the event will happen. And that's the whole issue. That's the whole crux of the problem. We don't know when it will happen. And so you have to make some decisions. So you need to list your critical items. My list is going to be different from your list, but you need to make the list and decide what you want to do. Much of what you have may be sacrificed, including air conditioners, vehicles, fridges. And like I said, we're dealing with a lot of unknowns. Even in today, the military has done a number of EMP tests. I know MIT has done a number of tests. As a matter of fact, 99% of the information that I am using is from a couple of MIT people who did nothing but test EMP and CME protection. In particular, when we start talking about Faraday cages, I'll be using real science and not YouTube videos, okay? So much of the equipment will be sacrificed. You just have to assume that you can't protect everything. You have to use Faraday cages to protect electronic equipment from any type of electromagnetic signal. Faraday cages, the whole idea of a Faraday cage is to attenuate or suppress the EMP pulse down to a level that the device can tolerate. And I'm getting to the point in this presentation where it's really another 45 minutes talking detailed about the Faraday cage, and I think I'm going to hold that off to another presentation. I just want to go ahead and finish the discussion and give a brief 60,000 foot view of Faraday cages and how to protect against HEMP or CME. Okay, so the first thing that you need to protect against, the most important thing is this E1 pulse, right? And what you need to do is you need to determine how much attenuation you need in order to protect your devices. And in order for that, you need to determine the voltage level that could be induced into the equipment. And as we all know, with inductors and capacitors, electricity can be inducted into a circuit, right? You don't have to have a battery directly connected to wires. It can be induced from currents. And so the same thing happens with the E1 pulse. We have to determine what voltage level is there. For example, again, without shielding, a simple 6-foot electrical cord could receive 100,000 volts. Your cell phone, your 4-inch cell phone, could receive a 5,000 volt. And again, remember what I said. This is all based on old data. This is when we were dealing with the HEMPs that the United States was able to produce, Starfish Prime in particular. We saw we saw when that happened, Hawaii, a lot of their devices went down. And that was some 1,200 miles away from the event. There's just so much stuff that we don't know now with the advent of the new people building devices. So again, this is all based on old information. The E1 pulse is, of course, too fast for normal commercial transient spike protectors to handle. However, there is a company called EMP, I'll think of it, that they say that their devices are quick enough to take care of the E1 pulse. They have a device that you can hook to your car, also to your house. that's supposed to protect that. I don't know if it does it. They say it does it. They have quote unquote certifications that it works. So maybe that is a something that we could take a look at. But barring that device, I know of no other commercial transient spike protector to handle an E1 pulse, the 5 nanosecond transient time for it to create a 50,000 volt per square meter shocker, right? So, and then we have, of course, the E2 pulse. It overlaps the E1, resembling a lightning strike. It'll induce 100 volts per square meter, and because it happens after the E1, the spike protection goes away because you've defeated that with the E1, which means that you'll also get a shock with the E2, providing this new device, this EMP. And one of these times I'll remember the name of it. I think other people know. If they want to put it in the comments, they can certainly do that. So then, of course, we have the E3. This is the stuff that if we just had a CME, we can really effectively protect against that. Now, the electrical systems are still going to have problems. Our big transformers could still fry because, again, we're dealing with quasi-DC voltages on AC transformers. That does not, it's like mixing oil and water. It's not meant to do that. So there's going to be a lot of snap, crackle, pop on the power grid if a CME were to directly hit the Earth. And we already know of current near misses. You know, Canada, they had a big portion of their system went down because of a CME. There was a couple other instances where we weren't hit direct on, but if we do, you know, things can start going snap, crackle, pop. This E3 pulse produced by the CME, all you got to do pretty much is unplug your devices from your outlet, hit the breaker to your main house to disconnect yourself from the grid, and you've done a huge amount of self-protection. And so if we just had a CME and if we just had to deal with the E3 pulse, you know, we're going to be able to take care of the majority of issues. But if it's part of an EMP or an HEMP, then things are already destroyed and it really doesn't matter. So the device is probably already toast if it's part of an EMP. So the question is, how much is enough? How much suppression do I need? And the shielding effectiveness can actually be calculated. And it's the case of the amplitude ratio is what we're looking to deal with. And so, for example, if an EMP is 50,000 volts per square meter, and we'd like the container to reduce it inside to 5 volts per meter, then the amplitude ratio would be 50,000 volts divided by the meters, divided by 5 volts per meter, and so it's 10,000, and you put that in the equation, and you know, we deal with decibels as what we use to calculate the suppression level. And so we would need a container to attenuate the 50,000 volts by 80 dB. As a matter of fact, here is a chart of what you can do and what each level of decibels allow. So here's the amplitude ratio of 10,000, bringing it down to 5 volts per meter. So that brings it down to 1.5 volts per foot. My cell phone can easily handle that. And there's volts per inch, right? So if we are only able to attenuate it to 20 dB, then you can see, you can read along there. And so this kind of gives you an idea of how much you need to suppress the voltages in your container, in your Faraday cage. But we're going to actually, let's go through a couple of examples going through this. So here I have a 4-inch cell phone. It's placed in a container which only has a 30 dB of shielding. Then the phone would receive an induced voltage equal to about 160 volts. It would fry my phone. So 30 dB ain't going to work. The microchips inside the phone is typically good for about 10 volts, not 160. So, of course, the phone would be destroyed. Example number 2, if a power hand drill with that's about 1 foot large with the power cord wrapped around it was placed in the same container, then it would receive a pulse equal to less than 500 volts, which the item would probably survive because it is an electric motor and it typically could survive a 600 volt spike. Example number 3 is if the power drill had a 7-foot cord on it and it was not wrapped, then that the induced voltage would be 3,800 volts, and of course you would just have a paperweight with a 7-foot cord on it. So the insulation on the motor is good for about 600 volts, like I said, but once you get past there, arcs happen and the drill is now damaged. And the last example, if the same drill with the cord wrapped around it now is placed in a 55-gallon barrel with a 76 dB suppression, the drill would see a pulse between 1.5 and 5 volts, well within the protection ratings of the drill. So that would be good. So the size, type of equipment, and container suppression levels matter. All 3 of those parameters must be taken into account to ensure the protection of the equipment. And this is the thing where we're going to separate the famous YouTube videos of how can I protect my equipment by doing these silly things. They only take one thing into account, and even that is laughable. Also, if an object is placed in multiple containers, then the resulting protection is the sum of the suppression of each container. So you can use that to your advantage. So again, I'm just warning here that super EMPs are now capable of producing 200,000 volts, which we still need to take into account. All of the other math works. You just need to plug in 200,000 instead of 50,000, right? So we have things that, we're going to have to use a combination of containers if we're going to protect against a 200K kV issue. So let's just talk. I'm not going to get into detail about Faraday cages, but I'm going to talk about why Faraday cages work, okay? So the whole issue with shielding comes down to the size of the hole. EMP pulse shielding requires the equipment surrounded by a continuous electrical conducting metallic container with very few, if any, holes. And the holes need to be very, very small, if any. So if you have a container that's a mil thick of aluminum, it can provide 94 dB suppression. Providing there are no holes allowing leakage, that would be a viable option. So the amount of leakage of energy into the container is primarily determined by the signal wavelength and the relative size of the holes in the shield. And so these two things are critical. This is the thing that is never dealt with on YouTube, the signal wavelength. YouTube always deals, the people that I see always deal with the size of the holes, right? They'll go ahead and use tape and they'll tape everything up, but they're not looking at the wavelength. And we'll see in a couple of slides, the EMP pulse does not produce just a single wavelength. There's a huge range of wavelengths that your shield needs to protect against. We're going to talk about that. So the sum and size of the holes must be hundreds of times smaller than the wavelength of the signal in order to suppress an E1 pulse sufficiently to protect the equipment inside. And here's the number one example of a Faraday cage that everybody has in their home, and that is, yes, the microwave oven, right? So you look at the glass door of a microwave oven, it has about 50 holes per square inch, okay? Each of the holes is about 1.2 millimeters large. And I'm going to show a table that lets us see why we're able to see our food that's cooking, but as we're looking at it, we're not feeling the effects of the microwave radiation. And all that has to do with wavelengths. So here's the microwave oven. The frequency is almost 2.5 gigahertz. The wavelength is 122 millimeters. And so the ratio of the wavelength to the oven hole size, that 1.2 millimeters, is 100. And so that's why we can look in the microwave oven to see our food cook and not our eyes cooking, is because of this issue right here. And if you look at various items, an FM radio, a cell phone, cordless phone, AM radio, they are based on different frequencies that you would have to, if you want to protect your equipment from FM radio, then you are in the megahertz range, right? A cell phone is in the gigahertz range. A cordless phone is 1.92. As a matter of fact, you can look in any number of YouTube videos, and they'll put a cell phone inside of a garbage can and call the cell phone, and the cell phone will not ring. And they say, see, my Faraday cage works. Well, okay, we're going to talk about that. So, the table shows that in order to determine the signal suppression of a Faraday cage, it's necessary to examine the effective frequency and wavelength of the signals versus the size and quantity of the holes, which allow leakage. In other words, the size of the holes, the frequency of the pulse, and the quantity of holes determine the effectiveness of a Faraday cage. And the military has defined minimum dB shielding required at different frequencies, and this is a graph that shows this. Okay, so an EMP happens way down here in the 100 kilohertz range, all the way up to 10 gigahertz. And you have to protect your equipment against all of these frequency ranges and not just one. YouTube is full of brilliant scientists who are only controlling one particular range, and this is why their system is not going to work. And so, here's a warning. And I've already talked about this. Several persons have posted videos on the internet demonstrating their measurements of metal garbage cans when used as a Faraday cage. They put their AM or FM radio in the garbage can, they close the tight-lidding lid and the radio stops playing. They conclude, therefore, that they've demonstrated their metal garbage can is a good Faraday cage for EMPs. Not so. Their garbage can will be worthless in protecting against higher EMP frequencies in the range of 10 megahertz to 1 gigahertz, and as a result, the contents that is inside their garbage can will be fried by any typical EMP. But there is good news to this. The good news is that their destroyed devices will already be in the garbage can. There's also a huge issue on YouTube where, I'm just going to this will be the last thing that I talk about. An EMP can induce, this is old news now, 50,000 volts per meter on the walls of the container. If I had a 80 dB of shielding, then the inside of the contents would remain at a 5 volts per meter, and that's great. However, there's a 45,000 volt per meter difference between the two. Remember that. Typically, 10 kV to 30 kV can arc across a 1-inch air gap depending on air pressure, particulate content, and humidity. The difference of 3,000 volts can easily arc between two items when separated by 0.2 inches. Now, what's 0.2 inches? Well, that would be cardboard. As a matter of fact, the devices need to be surrounded by anti-static or other high-resistant material to prevent arcing from them, from the container wall. So you not only need to have the appropriate container, but you also have to have an anti-static bag and space or distance between your devices and the surrounding container, whatever that is. And if the lid does not need to be insulated, provided you have at least 2 inches of space between the equipment. If it's, however, filled to the top, then you also need to isolate the lid from the contents. And so here's a couple of things, and when you download the PDF of this, all this will be there for you. Let's see. And so again, talking about the internet and the misinformation that's there, they always show a simple cardboard that is protecting your devices to the outside container. Cardboard is not much better than air, and you will get a 5,000 volt arc between the contents and the inside. And so you got to make sure that we are using material that's at least 1 inch, preferably 2 inches, all the way around to separate the outside skin to the inside, plus using your anti-static bags. So without that, your equipment will be fried. And that's all I'm going to talk about as far as Faraday cages go. It is, boy, time has flown. Let me go ahead and stop the share, and I'd like to have a conversation with everybody now, answer questions or whatever everybody wants to do. Again, there's a whole other section on Faraday cages. I just gave you a taste of what needs to happen. So
First, we'll go to Barry. Barry, you want to go give us an idea what's going on in the chat?
So a lot of good comments. So a 10-gallon can inside a 33-gallon garbage can, will that work with insulation?
as long as you have the separation intact, okay, that the largest can, if you just have cans stacked on one another, you're not going to do anything. You're going to carry that current all the way into the smaller can. It has to be separated. It has to be isolated. And if you have multiple isolation cans, then yes, then you add the attenuation between each container.
So about a 2-inch insulation then would be good?
Oh yeah. Yeah, 2-inch insulation on the first one, 1 inch probably on the second one. And as long as you control the hole size, right? Again, we're dealing with multiple frequencies. So the rule of thumb is to produce a container that will hold water. And if you turn the container all the way around and you have zero leakage, then you're probably good.
And thermo chamber tests are commonly used to determine effectiveness of shielding. I don't know what that is.
I didn't understand.
Thermo chamber test. I guess it's some kind of a test. Check about the effectiveness of the shielding. Tim, do you want to come on and explain
in the
that?
chat?
Yeah, I'm looking in the chat, and as I'm looking there,
There we go.
EMP
Now I'm
shield.
unmuted. Now I'm unmuted. Yeah, I work for the Department of Defense. I'm a senior scientist, and one of the thermal chamber test, what it is, it's a great way to test for shielding effectiveness, and especially at all frequencies that you mentioned. What it is, you take a big anechoic chamber, and there's a paddle on that hangs from the ceiling, and then you radiate, you send radiation from various frequencies, and the paddle turns because you got also, and then you got another box within that chamber, and it's sealed on all sides except for an opening. So you put your material there, whatever, and the paddle turns at different angles, and so you get different orientations of the RF energy. And then they do that to determine how effective really is something to shielding that you're mentioning from all types of, because the RF energy has, besides the frequency, you got to have the orientation element of RF energy. And so that's a
Absolutely.
common test you do to determine the effectiveness of shielding. Is they call it the thermo chamber test.
Yep. And actually, the gentleman that I've been working with at MIT, they use that, and along with other things. And so, yeah, you're right on.
That's everything,
Okay, so I share that test with you.
Anthony. We have some people with hands raised, though.
Yeah, go ahead, Paul.
Yeah, I'm thinking each disaster makes its own rules, and the first rule is there are no rules. So I'm thinking we should probably each do the best that we can, and it's possible if we're not directly hit, but we're on the fringe, maybe our best might work out. You never know. I mean, each
Well,
disaster.
this is the big unknown, however, and I agree with you 100%. It used to be that they said every vehicle will just stop, other than the vehicles created in 1970 and earlier, or maybe it's 1981, or whenever they stopped putting in spark plugs, right? Or everybody knows what I'm talking about, right?
Right.
Electronic ignition.
Yeah, exactly. Now, it might be that your next door neighbor's car won't work, but your car will work. I mean, there are just so many variables that are unknown. And so, and I agree with you 100%. We do the best we can, but let's put the best we can in our favor and not deal with misinformation, right?
Right. So the guy that proved that his FM radio was good, well, that's great for his FM radio, but my high frequency radio is toast.
Well, that's not good on his FM radio because he's only testing a certain frequency,
Oh, okay.
the FM radio frequency. Okay. And so, yes, you got to be careful, buyer beware type of thing. You need to, and this is why we have these things at RATPAC, so we can explore all of these other issues that are out there. I mean,
So somebody asked if you could get a cloth-like bag that would do something.
yes, absolutely. So long as you have no holes in the bag. Okay. They make Faraday cloth. Some of it can be very, very expensive. It's weaved with stainless steel. Those spaces between the stainless steel and the fibers are really, really small. It might work. It might not work. The problem is you're not going to be able to sue the company when it doesn't work, right? They've already got their money. If an EMP happens, that's going to be the last of my worries, is suing anybody.
Like your
right?
25-year-old rotten freeze-dried food. Eh?
Yeah, I'm going to be worrying about getting clean water for my family and food, right? And so, the heck with everybody else. So the best we can do is the best we can do.
What about the EMP duffel bags that I've seen them sell?
Especially if they're in, like, for example, and I generally don't volunteer this information, but I'm going to because this is RATPAC. I have a big safe. It's a 1/4 inch thick. The skin of it is a 1/4 inch thick. It weighs 2 tons. It's massive. And in that safe, I have another safe that I put my electronics in, okay, that I want to save. I think it will survive an EMP. I don't know. Hopefully it does. Hopefully there's enough. I've attenuated the signal enough for it to happen. But you need to remember the stuff that you're protecting you can't use on a day-to-day basis because I'm not downstairs in my office going into the safe every single day. I have radios in my truck, in my car, in my backpack, my go kits. I only have a few radios in my EMP protection location, right? And so I'm going to assume that probably most of the stuff is going to be fried. Maybe some of it will work. There's just no way of knowing until it happens. And I hope it never happens.
Barry, I'm sorry, Marty, go ahead, please.
Oh, thanks. Great talk, Dan. A couple things. First, for those who haven't read it, Dennis Bodson, the late past director from the Roanoke Division for ARRL, was a scientist for the feds and has a 4-part article series on EMP protection back in QST back in the I think the 80s or early 90s, I think late 80s. So it's a good source just to, and you'll see some of the stuff that Dan talked about in there. One of the things that he pointed out is that in at least the EMPs they were studying at the time, probably 90 to 95% of the energy was below 100 megahertz, which would suggest that VHF equipment might, if have some adequate protection, would be receiving a lot less energy than HF stuff. But my question is first with the does the inverse squared wave law apply here, where if you're on the fringes of it, you're going to get a substantially weakened pulse from what was generated at the blast source?
Right. There is a definite difference between the distance of ground zero, if you will, even though ground zero is 300 miles above you.
The slant distance, yeah.
The slant distance, but we're still dealing with tens of thousands of volts at the fringe area.
Okay, even there. Okay.
Yeah.
And the other thing is, many of us have gone to lithium iron phosphate batteries, which of course have a battery management system, which has devices with small gaps in them, and that's going to die. But what about a good old fashioned lead acid, cell like the ones that they use at the phone company central offices?
I don't know what the lead plates are going to do if they're going to arc one to another. I have no idea. What are those lead acid batteries made out of? They're made out of lead plates, right?
Yeah.
And are they close enough to have it destroyed? There's just no way of knowing.
Okay, thanks.
Yeah.
Kyle in Idaho.
Thanks, Dan. I have heard many discussions on this topic, and Dan, this is an excellent one. I look forward to part 2. But I have a rhetorical question, and I submit it only because it can't be answered. But we could strategize, and I've never heard it addressed. Let's say we do the best job possible, and after the attack, we're in pretty good shape. Much of the stuff that we've protected is functional. Here's the problem. How do you know when it's safe to take it out and use it?
Right. And here's the rule of thumb. If the government, which they're not going to tell us, if we see that blinding flash, because we will be able to see. Now, we may not be able to see it if it goes, like I'm in Utah. I don't know if I'll be able to see it in Nebraska, 300 miles up. I might. I don't know. If that happens, whatever is destroyed at the time, it is what it is. So I can control E3 type of waves. I can start putting things, and if things work, then I'm going to unplug myself from the electrical grid, because that I have time to do that, right? The question is, will my other stuff already be fried? I don't know that yet. But when I unplug myself, I'm going to wait for a number of days before I do anything. And I'm not going to get my radio out right off the bat, because there could be subsequent bad actors doing the same thing. The one thing that the military knows is, in order for something like this to happen, all the bad guys already know that just a single attack, maybe to the East Coast, or just a single EMP bomb is not going to probably take the U.S. down. It's going to be a three-prong attack. So I'm thinking they're going to wait for a Yellowstone earthquake, or the destruction there, or some massive disaster happening in one part of the country where the U.S. is moving their resources to them, and then something else happens, and then you get two container ships that are throwing up thermonuclear bombs trying to get above Nebraska. That's the best place to do it, to take care of the entire U.S. Maybe you have North Korea that only wants to just be right above Washington, D.C. There's no way of knowing what the bad actors' plans are, right? And we don't know how many of them would it would be foolish for each one of them to be working in isolation. You know that they're going to be trying to work together. Right? I mean, this is just military common sense, and this is what the military is assuming will happen. And so you always wait a number of days before you take anything out of your EMP-proof stuff. And that's what I'm going to do, is wait. Because if it's going to happen, it's going to happen within a day, 24 hours of each other. Okay? And I'm not talking about a chemical warfare on the East Coast versus the same time having some type of chemical warfare on the West Coast, the same time having another balloon from China go over Montana and deliver its goods, at the same time other things that are happening. I'm going to wait until 48 hours before I do anything. And everybody that I've talked to, both in the military and at my friends at MIT, they all concede about the same thing. 48 hours, don't touch it, because it could happen within that time frame. After 48 hours, if my electronic watch still isn't working and nothing else has happened, then I'll go ahead and start seeing how bad things are. By then, I will have already been able to get ready. I'll need to know. I will already know if I need to bug out or bug in, if you will. And that's another presentation of what you do after a disaster, right? But my rule of thumb is 48 hours after the event before I pull anything out of protection.
Thanks very much. Yeah, I'd like to discuss this
Yeah.
at length in other venues, and perhaps maybe again with you at some point. But
Sure.
yeah, I think it's equally important, the after strategy as well as the pre-strategy.
Yep.
Thanks, Kyle. Paul, go ahead.
I can't remember.
I'm sorry. Kilo Foxtrot 7, Sierra Oscar Juliet.
That's Paul in Montana. That's me. Anyway, I'm just wondering, with these with the high bombs that they've got, are we going to survive if an EMP on our bodies? We are.
Oh yeah, they are.
A lot of highly conductive liquid.
Right. So there is no physical or infrastructure damage on a high altitude EMP. Okay, so that's the good news. Even people with pacemakers, they are guessing that the majority of those people will be okay. That's not where the problem is. The problem is those people who are on respirators and things that are in the hospital, where you have other things that aren't protected against an EMP. That's why there's going to be so much death in the first 48 hours, is because those people will go first. Then, after your refrigeration goes and you run out of insulin, and people who are that require the grid to survive, those people are the first people to go, unfortunately, right? And that's where the death comes. It's the lack of the grid powering the stuff that would normally keep us alive, right? So our bodies, there's going to be zero radioactivity involved. We already know that. That's been tested. So no physical damage to our bodies or to the infrastructure. As far as physical things getting blown up, the problem is the electronic stuff gets all blown up.
I was
So,
thinking the electricity generated in our bodies.
yeah, nope, nope, you're good. You're good.
Okay.
And don't sue me in case I'm wrong.
You'll be the first one on the.
Everybody says that. Well, we already know that to be the case because we've had a number of HEMPs already run. Star Primefish was a great example, and that's where they determined. Yeah, they saw the detonation, but physically you were okay. There was no radiation, no gamma rays. The gamma rays are the thing that knocked the electrons out. The Compton effect happened. The problem is with the electronics being fried by the high voltages that are induced by the Compton effect. So you get the Compton current.
Ted, go ahead, please. You're still muted there, Ted. There you go.
Hi, how you doing? I heard Ken. Okay, W2TED, and my business is radio broadcasting, and I've looked at some of the things that have been done for the PEP stations for AM broadcastings in the emergency alert system. And one of the things that occurred to me is that when we look at our ham antennas, and we look at what happened in a recent lightning strike at my house, we won't have any HF antennas that were up. The pulse that is delivered just by lightning, much less an EMP, which is at least 3 orders of magnitude greater, is going to frazzle any piece of copper weld wire you've got up there, break every ferrite core in a ballon, and render your antennas non-existent. And if you leave the wires coiled up on the ground, you're going to end up with lots of arcs and everything else on the wires, and you may not have a coiled up antenna able to work after you have incurred an EMP. The other thing that does occur to me is that the first level of protection of structures, meaning grounds and antennas and passives, that is needed for lightning will probably not survive an EMP, but properly it's putting your grounds together, single point grounds in your house and stuff like that, will certainly be more likely for you to survive touching a faucet or a piece of metal in your house that's grounded if it's grounded properly with single point grounds.
Okay, let me stop you right there. That is true with an E3. Okay, it will kill you in an E1. One of the misinformation things that you find on YouTube is, yeah, you want to ground everything. Okay, well, that's great if you're dealing with the CME. As a matter of fact, I don't want to ground. I want to bring everything isolated from everything else. I do not want to touch the ground. Okay, I want to be completely isolated, and I might be a capacitor for an hour or so, but I'm okay with that as long as I'm not. I hear people say run a ground wire to your trash can, your 55-gallon trash can, to a ground rod. No. Oh, well, you can if you want to destroy everything in there, because you need to remember the E1 and the E2 rely on the longer the conductor is, you get more voltage induced onto that conductor. So you do not want to ground it. That only works for E3. So if we're just dealing with the CME, I can think about grounding it, but even with the CME, I'm bringing everything in. And I know I'm going to lose my HF antenna. That's why I have a half-wave end-fed in my safe. Okay, it's one of those things where I'm going to assume that will be there. It may not work. I don't know that, but I'm crossing my fingers. So grounding is a big no-no, protecting against the EMP.
Right. Okay. The other thing is the aspect that after an EMP, you won't have any skywave communication for a day or two at least.
It'll be a while.
8 hours that you were talking about is don't even try to start playing around with HF. It's going to take hours before VHF even works, because the total amount of noise from the ionization of the ionosphere up into the VHF bands are going to be very exceeding.
Horrible. Yeah.
You aren't going to be able to communicate for probably 24 hours on UHF, maybe 48 hours on VHF, and maybe 3 days on HF.
The only radio communications I'm going to do post EMP is receive only. I'm going to use my single sideband receivers after the 48 hours and get them going. Okay, I'm not going to transmit until I get intel. Okay, the worst thing you can do is identify that there's survivors in a particular place, right? This is just military 101, right? You don't want to broadcast where you're at and how well off you are. That is a bad mistake.
Yeah, and it used to be the frequency hopping was a good thing, but narrowband frequency hopping doesn't work when you've got waterfall displays on.
Right, exactly.
So you end up with the problem that you're giving yourself away, even using the Korean War technology. So it's not a small task.
Right. And we've been talking about the worst case scenario. An EMP from a bad actor is like the worst case scenario that the U.S. can go against, right? In my opinion, this is Dan Lundwall's opinion only, N7XDL's opinion. I am going to put 80% of my efforts in things that there's an 80% probability of happening. In my case, it's a 7.5 earthquake. The EMP will happen. The probability is there. It's not zero, but it's way lower than other things I need to worry about. So I have a minimal amount of equipment that is prepared for an EMP. Okay. The rest of the stuff I'm dealing with preparing for stuff that there's a higher probability. So, I want to be able to sleep at night, right? There's only so much stuff you can do and prepare. So, But anyway.
Yeah. So for example, the W4 folks, they need to worry about hurricanes more than they need to worry about EMP. And then there's also the possibility that there are small actors like, for example, Iran and North Korea, who are likely to deploy tactical nukes as opposed to the thermonuclear weapons that would do an EMP over a large area. So you could deploy a 50-mile up atomic bomb over DC and shut down the government very nicely.
Right.
But to make a hydrogen bomb, I mean, there's what 6 actors that have them.
Right.
So
We'll go ahead over to Tom, W3 Tango Delta Hotel.
Thank you, sir. My question is that I'm a retired electrician. If I were to go and get rid of all my plastic covered cables and revert to the metal jacketed and metal conduit type things, and make sure I had my grounds for the electrical purpose inside that stuff, not use the outside metal for grounding, would I do myself any good, or is that just a hell of a way to waste time?
I don't know the answer to that particular. I understand the concept, putting your coax inside of a metal conduit. I don't know what I do know that the Compton effect, it doesn't matter where that is, it goes. I just don't know. I'm going to be honest with you. Cross your fingers.
Okay. Back to you, Barry, with the chat. Anything?
Okay, yes. Elizabeth wants to know, does the U.S. government test an emergency alert to the public so you can put your cell phone into a Faraday bag? I don't think it would make any difference because the cell towers would all be gone, so the cell phones would probably be useless. But do they do that?
There is a scenario in the government where they would warn the people, the EMS system would be activated, but that is a much lower probability than having 3 or 4 actors sending up nukes and taking action before the government even realizes what's going on. I don't think that would ever happen. I don't think that you will get time. Now, a CME is a completely different thing. We have a day or two to prepare for that. Okay, we can see it coming, and we will know way ahead of time, hours and hours before it hits, to prepare for a CME. But an EMP, we won't get that chance.
So they used to have 640 and 1240 for.
I'm sorry?
That's what they used to have 640 and 1240 for.
Oh, yeah, exactly.
Are Faraday bags any good for cell phones?
Yes, so long as you follow the rules of a Faraday bag. And again, we haven't really we've talked about the basics of Faraday cages. The Faraday bag conversation comes in the next presentation. So when you want to have me back, I can talk about that.
Okay. Let's see.
But yes, even wrapping your cell phone in aluminum foil, so you need to control the holes and the ability for the wave to enter into whatever device you're protecting against. So if you have cell phones that you don't touch and you want to wrap it up, tape it up, not with cellophane tape, but with metal tape, and it has to be a particular kind of metallic tape, because even the glue needs to be conductive. Okay, you just don't use adhesive. It's a special 3M tape that you use for that. Yes, then you could do it, but you have to do it now and put it in a container and not use it until after the EMP event. So therein lies the problem. And again, further discussion will be in the Faraday cage presentation.
And if we had to, we could always go back to the old-fashioned technique of relaying messages by VHF.
Well, for the first little bit, it's going to be relaying messages as you walk next door to your neighbor.
Right. Okay, let's see what else.
Or how many people have bicycles, you know? I'm going to assume my motorcycle and my vehicles will not work, but bicycles don't require any electrical stuff, so that's why I ride a bike.
As long as it's not an electric bike.
The electric bike's not going to do you any good.
What will the effect of EMP on satellites?
Oh, they've when they were doing the testing, they knocked out a number of satellites up in the upper atmosphere, and you get a bad actor that understands EMPs, and they all do. There is a portion around the Earth where there's a reason why we have so many satellites in given regions, because if you go further out, we have everybody's heard of the Van Allen belt, right? Very highly charged particles around that area. Well, there's similar belts that are around the Earth, and they will not fly satellites in there. So bad actors already know where to do their detonation, and they'll probably know which satellites they'll take out. Now, how close a satellite has to be is another story. The fact that they're both up in the low Earth orbit, which is 120 miles to 150 miles to 300 miles, which is your goal to detonate if you want the entire U.S. to be affected. Anything that is line of sight could be affected, and those satellites could be knocked out if they are not EMP proof. Okay. So we're going to lose a lot of comms. We're going to lose a lot of communication from that. A lot of military satellites are, but most are not.
Right. Can you talk a little bit more about the home EMP, the EMP shield for a home that can be purchased for $400?
Yes. So EMP shield, they say that their transient spike receptors can do sub 5 nanosecond responses. Okay, if that's the case, then I'm all for it. What I don't understand is how that will protect my cell phone on my desk. Even if I'm plugged into a wall wart, I don't understand how an EMP shield can protect other electronics inside the home. So I really don't know. That's a huge question mark. Now, as far as putting it in my vehicle, I think it's worth the $300 just to have it there. It may or may not work. I don't know because there's so many other controllers that I don't know how connected they are to like the EMP shield for the home. It's on the neutral and the hot and the ground. They have the connectors that go to each one of those, but I don't know how they're protected to other than the power supply, because you don't have direct connection from your CPU on your phone to the power supply, the battery that runs your phone. Ultimately, it gets there, but there's a number of methods for that electron path to take place. So I just don't know how an EMP shield will protect it. That's why I don't have one. There's too many unknowns for that. And I refuse to listen to the marketeering material. I want to talk to my military friends and my friends at MIT to test that before I say that it'll work. So they say it will. Hopefully it does. And if you have one, I won't even be able to ask you if it worked after an EMP attack. So, good luck.
Here's an interesting question. This is the last one. Will flying planes fall out of the sky?
Many of them will. Many of them will. A lot of them are fly-by-wire. There's no, other than the A-10 Warthog, most of our aircraft are all electronics. Now, I know that many airlines are supposed to have shielded them, and they are pretty well shielded. Any one of them can hit a direct lightning strike, but that is a minuscule amount of energy compared to an E1 pulse. And so I don't know I do know the military thinks that commercial flights will just fall from the sky.
Thank you, Dan. We will be seeing you again next week. Again, everyone, thanks for coming to RATPAC tonight. This session is being recorded and will be posted in the next 2 to 3 days. Again, www.ratpac.us will get you all the information. Also, you may want to consider signing up for the Groups IO mailings that we send out, so you'll get notification of upcoming sessions. Also, consider joining any of the social media sites that RATPAC also provides information to. Thank you, everyone. I'm going to go ahead and close the meeting, and we'll say goodbye to everyone.